than something like an ASCII code. That's kind of known as a one-hot representation. So Simon Thorpe was the guy who did who cut up a bunch of monkey brains. And then there's some other interesting neuroscience here. I've tried to give you guys a lot of URLs so that if you get interested in any of this stuff or any of this catches your interest, you can go and look at it. Or by the way, drop me an email if you want to talk about it, and we don't get a chance here. So how's your car do it, or your camera? Well, it uses something called a convolutional neural net. Remember I was talking about that? What is that? Well, it's just a network where it has these layers, and these layers do a convolution pooling. And basically what convolution does is it's a image processing operation. And then what pooling does is take the maximum value out of the middle of this, like right here, to try to provide invariance to things like rotation. Because like when I look at you, I want to recognize it's your face and it's you, whether or not you have your head like this or like that. You want to be invariant to rotation, in plane, out of plane, all of that kind of stuff. That's what that does. And then at the top of it, it starts out with this stuff, and it finds lines and things like that. And then at the top it says it's a dog, or whatever. And so kind of a little bit more schematic view of it would be, you have an image. There's a convolutional layer in this thing. It detects these. Remember I said it gets edges and stuff? And then it, as the network does more processing, it gets, like pieces of faces, and then it gets faces, and then you hand that to another classifier, and it says, oh, it's Sarah. So this is the way this stuff works. So the thing to take away from this is that you really want to have a representation for your data that composes, because it's way more powerful. And so if we think about network data, we have to think about that a little bit. So anyway, you also have to realize that if Wolfram starts talking about this stuff, it's probably pretty mainstream already. So look at his website. He actually has a convolutional neural net where it'll classify your images for you. But there's a lot more going on. So Skype has real-time speech translation now. Uses the same technology. So if you think that's impressive, which I kind of do, there's this company called Emotion, and there's a bunch of these companies. And what they do is they use machine learning object recognition to classify what their emotional state is. So it looks like this at the end of the day. You can tell if the person's happy, sad, angry, surprised, whatever, with some probability. And you can think, I'll show you in a second a better picture of that, but you can kind of, we always talk about privacy concerns. Think about what this could mean. How does it work? Well, there was an interesting thing that happened this week. This came out of Science has a special issue on AI this month that was published earlier this week, and in there is an article on this. So I got that this week. But basically, there's points on your face, and there's a whole theory about how that maps to your emotional state. And then what you do is you take a bunch of pictures of people, and you go happy, sad, and then you show examples to the machine, and it learns, and then it can predict what the person's mood is. And so in this case, there was a psychologist who had this technology and was just talking to her, and that was an assist. So that's interesting. But everybody's doing this, right? So even Twitter, and Twitter just acquired Wet Lab. This is Ryan Adams. Ryan Adams is a professor, machine learning professor at Harvard. That was his company, just got acquired. But more than that, just recently, even more recently, Twitter opened up an AI lab, just like Google, Baidu, Facebook, all of those guys. Okay, so that's all cool. That's just amazing stuff going on. So why is it happening now? So I think I mentioned this, but before 2006, people didn't know how to do this. The technology didn't exist. They thought it couldn't be done, right? And so why now? 3 reasons. Theoretical breakthroughs in 2006. So we learned how to, we didn't, these guys did, learn how to train deep neural networks. Technically what they solved is something called the vanishing gradient problem, and I'll talk about that with anybody who wants to talk about it. It's about how you train these things. Basically, you use something called gradient descent to optimize something. I'll show you later what that looks like. But these were the 3 guys. Jeff Hinton at Toronto, Yoshua Bengay at Montreal, and Jan LeCun at NYU. Jeff's part-time at Hinton. Jeff's part-time at Google now, and Jan is director of AI at Facebook, right? And Yoshua I think he's working with IBM, but he's still at Montreal. So these guys cracked this. More recently, some of their students did even more work in this area. There was a really nice kind of popularized press paper about this in the Chronicle called The Believers, and that's because these guys started doing this in the 80s, and it went out of favor 3 times. I mean, there were 3 nuclear winners on this technology, and these guys hung in there, and that article talks about it a little bit. So first thing was theoretical breakthroughs. This in 2006. Second thing was compute. I mean, when these guys were trying to do this, computers were millions of times too slow, literally millions. But now compute's faster. We have Hadoop, MapReduce kind of things, and we have GPU and open source code to drive it. Data sets, that's the third thing. You need data to train these things. Well, there's massive data sets at Google, Baidu, and all of these different places, and the network, by the way. And there's this convergence of machine learning theory and practice. It's kind of interesting, really. In machine learning, the best coders and the best implementers are the theorists. You never see that. Usually there's some distance between them, but there isn't. So the latest theory that gets cracked comes out in Google product, the next week or something. So there's also an alternative view. This is kind of interesting because this is going on in real time. So these guys, so I'm calling them LBH. This is LeCun, Bangoy, and Hinton, LBH. They wrote a really nice paper in Nature that overviewed what was going on in deep learning. So if you want to get an overview, grab that paper. It's nice. But Jürgen Schmidhuber is another guy. He wrote a kind of a scathing review of this. And then these guys, that's Jürgen. I gave those guys a picture. I had to give Jürgen a picture. And by the way, if you ever have a chance to hear him talk, definitely take him up. He's really entertaining. Or YouTube, right? And then these guys had a rebuttal. So this is all going on in real time. So if you want to see what's going on in the community, it's pretty interesting. So what about this GPU thing? Just an aside on this. This is so important to deep learning because the way you train these things is massively parallel and you need a lot of cores. So it turns out that NVIDIA, which you used to think was a graphics card company, really has a whole new business in AI. And so here's from their page. And basically the support for that's built into all of the open source frameworks, all of these, and more, and many more. There's millions of open source frameworks for ML. It's kind of a problem. Oh, by the way, you can get I don't know if you know this, but you can get these you can just get a GPU clusters on Amazon EC2 if you want, so you can use that to train these. And then, just as an aside, the machine learning community has this very strong and long-standing open source, open data, and open model kind of tradition or culture. It's kind of the open science thing. So, for example, if you want to publish a paper in any of the 3 important conferences, you have to open source your code, your data, and the models because otherwise nobody can reproduce it, right? So, all that's before we get to networking. So what kind of things are people thinking about? Well, I just pulled a couple of things from Nanox64. This was a talk about next-gen telemetry. And this is sort of complementing the Google or OpenConfig, right? So one piece of OpenConfig is that they want streaming data out of all the boxes, and they want everything, including ASIC registers to whatever else is going on in the thing, including everything you got from SNMP or whatever management you had. But people are starting to realize, and the point of this slide is, this was just one of the slides from this talk, that one, and this is the thing. People are starting to realize that there's just too much data and there's just too much here, and humans can't really process this in any reasonable way, so we need ML to do it. But if you had this, it would be state-of-the-art or beyond. Nobody has this right now. This is aspirational comment, right? And there's the pointer to where it is if you want it. This was from Anis and Josh's OpenConfig talk, but basically what's in there? Well, where do those rules come from, and where's that all come from? You need machine learning to get that. And that's sort of not exactly called out there, but that's what they have in mind. And there's their talk. And then, how many people know what NFV is? Everybody knows what that is, right? So there's OPNFV, which is an open source project to try to put together a distribution for NFV. Well, part of that is this thing. The fault predictor, right? And this fault predictor, well, here, let me back up. This fault predictor thing is just a machine learning component of this, right? And then they have this idea that there's going to be fault management, which is sort of like putting intelligence on top of learning. But It's all kind of part of the same thing. So if you want to take a deeper look at that, it's there. So, okay, so all that stuff, that's all interesting. So imagine this now. So first, look at the network kind of differently. Envision that the network is, we talk about sensor networkings, we're always thinking of, IoT or something, right? But actually, every counter, every packet, byte, error, whatever counter that you would have had in your MIB, every other counter that the box has, every piece of telemetry it has, environmental or otherwise, every piece of environmental telemetry from the data center, from wherever, those are all sensors. So just think of that as a giant sensor network. And then each sensor is just its own dimension, right, in this space, right? So this forms this really high-dimensional, real-valued vector space. These are giant vectors, if you think about it. And so I drew this little picture over there. It was just a big vector full of, a bunch of vectors full of data, right? And it's very high dimensions, right? So so if you have 100 counters, it's going to be 100-dimensional, right? But you're going to have thousands or millions. This causes a problem called cursive dimensionality. I'll talk a little bit more about that later. That's an interesting machine learning thing. But guess what? This is kind of exactly the kind of data we need to kind of analyze this with deep neural networks, because they like high-dimensional data and they like it to be real valued in a vector space. And there's a reason why these are more powerful. I'll say a little bit later about that, but people always ask, why isn't just statistical analysis machine learning? It is, but it's a weaker form. And if you want to learn a little bit more about that, there's a nice technical report there. Now, okay, say I have all that stuff. Now, what kind of capability would I want to dream up? So I'm hallucinating some of this stuff. Some of it we already built, but some of it's kind of like, what would you want to do? Okay, this is what you want to do. You'd want to be able to say, okay, some interface just flapped. This is going to cause A, B, and C, right? Like CPU utilization on some other gateway far away. And that'll cause you to black hole something because you'll drop routes, right? But it's machine learning, so remember, it's with some probability, right? It's not. And then you could visualize it. You could show somebody, okay, here's the probability distribution of this happening because you just had this event. And then you can go look at it. Or maybe you can have an automated way of going looking at it. But you want to do stuff like this. You want to be kind of predictive. You want to say, hey, I've learned that if this stuff happens, something like this can happen. And you want to also be able to generalize, and I'll talk a little bit about that in a second. So that's the kind of thing we want to be able to do with machine learning and networking, at least in the management plane. In the control plane, for example, you can do all kinds of other things. So I worked with Adrian and Daniel on some PCE stuff where you try to build better path selection. That's in the control plane. But this is kind of management plane style. So guess what? You can do this and a lot more. But you have to have the right data. By the way, if it's not in the data that you're collecting, it's not there, okay? So it has to be there. So you have to collect the right data. But this also has vast implications in the security space. And again, you have to be careful there because there's sort of an economic analysis, if you will, of this, because there's false positives and false negatives, and you have to balance how much those cost and how you can mitigate the cost of that if you make a mistake. So what was this dimensionality thing? Okay, so now the network's this giant, huge dimensional vector space, right? And so that's good, but what's the deal with that? Okay, so machine learning, as I just told you, is really good at uncovering hidden structure in high-dimensional spaces. Humans are really poor at that. In fact, I don't know very many people who can draw a picture of something that's four-dimensional. Very few people can draw a picture of something that's three-dimensional. So, we're not that good at it. I mean, sometimes I'm not good at 2 dimensions, but yeah, so humans aren't. So what's a dimension here? It's a direction in the vector space, but it means a feature, one of those counters, and it's its own dimension, right? And so here's an example, but this is back in so these guys are wanting to do handwriting recognition. So they have this data set called MixNIST, MNIST, and it's a large database, giant, and they're all handwritten digits, 0 to 9. And you're supposed to see how accurately you can predict which one is which, right? But when we're talking about dimensionality, they're tiny images, 28 by 28 pixels. But if you think about that, that's a 784-dimensional pixel space. It's giant and a little thing. So if you think 4K TV, that's almost 9 million dimensional space, the pixel space. So these are high-dimensional objects, right? Well, the network's like that too. So why do we care, though? Why do we care? Because this is not networking, right? Well, because the interesting and unseen relationships, you know, when we used to talk about, oh, this is correlated with that, that's a relationship in some high-dimensional space, and the correlation is something we learn by projecting that onto something we can understand. But this is where all the real action is. So there's a hitch, though. That's all cool, but here's the problem. So this is a curse of dimensionality. So basically what happens is if you thought, just think of it this way. I have a length of, something of length 10, and I have 1 point on that. If all of a sudden I put that in 2 dimensions, now it's 1, so there it's 1 in 10. Now it's 1 in 100 in 2 dimensions. Now it's 1 in 1,000 in 3 dimensions, and all of a sudden, you know, the thing is starting to grow exponentially. So it does 2 things, right? First off, the space is growing exponentially in the number of dimensions, and then it gets stretched out. So everything becomes equally distant apart, so you can't really use distance metrics to determine like how good the fit is. So kind of technically what you need is if you want to generalize locally, you need kind of representative examples. Like I would need, oh, there was congestion here. I need an actual example of that if I want to, from all the different variations. Now, what's wrong with that? Well, there could be an exponential number of them. That's the problem. Exponential number of variations. So local representations like that won't scale. You need basically a neural network. So the classical thing is you just hope that the function that you're trying to detect is smooth, or you make features which kind of make it smooth. But it's suboptimal because then you have humans doing all the real hard work, and you've really kind of not solved the problem. So the ways you can solve it are mechanical Turk. Who knows what that is? So there's a machine in the 18th century called a Turk. It was a chess-playing machine. The Turk really had a person in it. So it was a scam, right? So they take the Turk out, and the little person would play chess. Mechanical Turk is a sort of crowdsourcing way of paying people to do labeling and stuff like that. You can do deep learning, which we've been talking about. You can use distributed representations. We've talked a little bit about that. Unsupervised learning and a lot of other things. But this is, if you want to talk about this, pull me over. This is an interesting area. Oh, my friend Nassim Taleb also wrote a paper on this, but it's a completely different perspective. It's from the perspective of sort of a quant, you know, which is sort of the econ perspective, but it's the same thing, if you want to look at that. Okay, so that's, you know, what the excitement is. What is machine learning? I mean, I really haven't told you that, right? So I gave those other guys pictures, so I thought I'd give Andrew Ning a picture. Andrew's a professor at Stanford, co-founder of Coursera, was the guy who started Google Brains, now the guy who started Baidu Research. And basically what he said was, what this all comes down to is a lot of words, but it basically says, in machine learning, the learning algorithms are in principle simple, but the interesting and complex things come from the data itself, not from the learning algorithms. So the question is, can you learn that structure? Can you learn that what's interesting about that data set? And that's what machine learning is trying to do. If you say it another way, what machine learning is trying to do is discover the data generating distribution. So you kind of imagine that you got this massive bunch of data and there's some function somewhere generating that, and your job is to try to learn that. And you really don't care about the accuracy of the model on the training set, the data you have, because you can make it 100% by just memorizing it. What you really want to do is have it generalized so that you can take the next thing that you haven't seen and learn and predict something, right? So accuracy on examples we haven't seen, as opposed to accuracy on the training set. There's a name for this. If you memorize the training set, you'll get 100% accuracy on it, but your generalization error will be low because you can imagine it'd be some fancy function that touched every point on the training set, but no other points, right? So it doesn't generalize. That's called overfitting. So here's another way to look at this. When we write programs generally, what we do is we have a program that some humans written, and we have some data, and we put it in a computer, and it spits out something, right? But in machine learning, what you do is, at least in the supervised setting, is what you do is you have data, that's what you collected, and you have some notion of what the output is. So you have image dog, image cat, things like that, and then it outputs a program that detects that. So this is very different, really different paradigm. So one way to think about this is learning in the machine learning setting is basically, what happens is you build an algorithm that outputs a program that runs on kind of a specialized abstract computer, which can be a neural network. But the thing to notice here is this thing outputs code, which is essentially machine code for this. So how far is it from that to, Python or whatever, Not very. So here's a little more detail. This slide, I wasn't really sure about this. It's a kind of dense slide. How am I doing? Oh, wow, I'm not going to. Okay, so you know what I'm going to do? This is all interesting stuff, but I want to talk to you guys about the network piece of this. Here, let me tell you one thing on this. So basically what you do, what learning is, this is the really shocking thing. At least some people get shocked by this. What machine learning is an optimization problem where what you want to do is you want to find a set of parameters for your model that minimizes your prediction error on the training set. You use the training set as a proxy for the real world, and this is called empirical risk minimization, and that's what it is over there. But basically, it's a fancy way of saying I have a prediction that's f of x parameterized by whatever my current parameters are, and I know the answer, that's y. So I have a loss function that tells me, oh, you predicted this, it was this, here's the loss function. What you do is minimize. What you just do is you use what's basically optimization theory to minimize that. And that's how you learn. So what it does is tiny adjustments in the weights or the parameters of the model until you minimize it, right? So, and then there are three kinds of learning depending on how it works. So what can we do for, the network community? So, to get through this pretty quickly. Basically, this is what the normal stack looks like. You got to get data. You have to have data science people because data is really ugly and messy, and it's all noisy, and it's, mostly garbage. And so you have to process a little bit before you can get here. But we want to work up here. This stuff is not trivial, but we want to work up here. So if you look at a workflow kind of schematic, basically what you have here is you have an analytics platform. This is usually what people call an analytics platform. You have some learning stuff. I'm kind of going through this fast because I want to get to this other example. But learning isn't intelligence, right? So you need some basically logic that has to do with what you know about your environment, what your business logic and all of that other stuff is. And then you could do optimization, remediation, or Mike Dvorkin, intent, or you could use recommender systems to use an open loop here. And then you can have this whole feedback thing, right? I mean, the reason I put a recommender system there is because I don't think anybody will let this thing configure their network. Not for a while, anyway. So here's an example so you can just see I wanted to find a concrete example. So here's your goal. Suppose your goal is I want to build some tools for the DevOps folks. And what I wanted to do, again, it's kind of in the management plane, right? So I want to make it so I get deeper automation and I get new capabilities, and it's kind of an obvious ML thing, right? So one approach is take a couple of algorithms and see if you can put them together to give new inferences that you haven't seen that are useful. So the reason we chose these two is because they happen to be in Spark, ML Lib, and it was easy to write code for these, and it was trying to do a proof of concept here. So frequent pattern matching and k-means. I'll tell you what those are right now. So, if you want to talk about this local estimator stuff, which is really interesting, that's a part of machine learning called representation learning. It's a very interesting and hot area right now. Pull me over. I could talk about it. So let's briefly look at this so we can get to this. Okay, so what this frequent pattern mining thing was is it finds patterns in what's called categorical data. Categorical data is data that doesn't have any ordering. There's no ordering. So like if you have flow data and it tells you the protocol is UDP or TCP or ICMP, the difference between those is not meaningful. They're categorical. They're categories, right? So what FP mining does is it returns these item sets that are a group of transaction IDs. Just think of the data set as a big matrix. The transaction ID is the row number. And they're corresponding to some patterns. So I just wrote down what the code I wrote kind of writes out this kind of stuff. So you could have source, destination, source port, whatever. You could have application name. You could have anything you want in there, right? Depending on what data you built. And then k-means, what it does is it finds clusters, things that are of the same type in what's called continuous data. So this is data that the difference between 2 points is meaningful, like a Euclidean distance or something like that. And so it could be things like the group of records that have some congestion indicator in them. And you get it back in a set of these transaction IDs. right? So I just drew a graph of, I'll show you the code that does this in a second, but these are the clusters, and they're basically correspond to these transaction ID sets. And the reason I showed you this other thing is that real data is 3 or more dimensions, but if you want to visualize it, you have to project it onto something. Use something called PCA for that. If you want to know about that, I'd love to talk to you about that. But I'm just telling you this is because you'll see things in these plots that look like this, where the stuff bleeds over. And the reason why is because the real data is in a higher dimension and it's projected onto a lower dimension space, and so it kind of smears out. So here's something that's interesting. So you look at this and you go, okay, I can find patterns that are of some frequency. I can find events that cluster together. Well, if I do this simple inferencing, just do the intersection of those two sets. You know, what that is patterns that cluster together, right? And so you could say these application patterns occur with congestion because they cluster together with the congestion thing. That's something we don't have right now, right? And so that's kind of a little bit predictive, right? Weakly predictive, but it's weak because of the algorithms are actually kind of simple. But that thing is an example, and that's kind of only limited by what's in your data and what you can imagine doing. So how hard is it to code any of this stuff up, by the way? Is it hard? Well, this isn't Spark, Scala. There's Python, Java, and R. Take your choice. It has bindings for all of that if you like it. But essentially, you know, this is all the code that actually did it. The rest of it's just what's called ETL is just extract, transform, and load. Make the data useful for these algorithms. And I just showed you this up here because the Spark's there, my code's there, all this code's right there where it says code. And then there's a data set that I just used so you guys could play with this if you want. How about k-means? Well, same thing. It's just not that much. And code's there again. So, you know, basically over here what I did was I printed this X thing where the middle of the cluster was, so you can see that there's kind of 3 clusters there. Okay, so what kind of things would you do? You get data, obviously. And then what we did was we collected network and endpoint information, environmental set, all that stuff I was talking about, Puppet, Chef, recipes, everything that's surrounding the network. And then we can use this pipeline, so do this FP thing, then do k-means, then do the intersection, to kind of learn interesting things. But these are very static, so you could get the flow characteristics, time of day, volume, all that kind of stuff. And we're kind of only limited by what we can dream up here, you know, and of course whatever's in the data, because as I said earlier, if the stuff isn't in your data, it's not going to get created by this. You can discover it if it's there, you can't make it. Well, if you can make it, something else is wrong. So these are primarily descriptive though, right? This is sort of like reactive. I found this, okay, that's what's in there. But you could do something else too, which is kind of, I think, more interesting, is you can use the same pipeline but do it predictively, right? So you could analyze changes and try to predict possible behavior. Now, remember, this is all with some probability because machine learning algorithms build probabilistic models, right? So you could say, if you make this ACL, routing, QoS, whatever change, it's going to cause some kind of event. I'm just saying, calling it X, because there can be many different kinds, with some probability. Or you could say, if you configure this application, call it X, with some parameters, there's some probability that you'll get congestion. You can continue, you know. You can look at queues dropping, percentages of packets when you have applications talking in certain ways. And you can also do other kinds of things, like you can use that same data to train new instances. And you can recognize kind of application and behavior in kind of real time, which is useful. So you could do things like anomaly detection. In k-means, what anomaly detection means is if there's some points that are really far from all those clusters, you can go take a look at that. And something's going on there, right? Maybe that your algorithm's broken, but it may not. And then you can use something else like Gaussian multivariate anomaly detection, which is a really simple thing to kind of zone in on what the real problem is, if there is one. And all of this can be made real time. In fact, in Spark, where we were doing all of this stuff, they have Spark Streaming, which just does this. Oh, wow, I'm out of time. Okay, let me do my last slide, and then I think this is my last slide. Okay, so some of what the future's about. so all those technologies that the k-means and the pattern matching are really, really low end and not too powerful in terms of their sort of algorithmic power. But we're going to get the really powerful algorithms coming to networking now. So these are deep neural networks. And remember, these other things, what they do is they're statistical models that learn simple patterns and stuff. The deep neural networks, they learn a function or a computation, which is quite a bit different. There'll be a lot more emphasis on control. Now, our network's about control. A lot of it's about control. If you look at, I got to recognize objects in an image, that's kind of a static thing. So we're going to use other kinds of networks for this, like recurrent neural networks that I was talking about earlier, which can model time series and long-range dependencies, and reinforcement learning, which is, here's a picture of it. Basically what you do is you try to optimize your maximum reward in the future. That's how robots work. Machine learning is going to be doing all kinds of unexpected networking tasks. And usually when I say networking, I mean compute, storage, networking, security, and energy. Who thought we'd have self-driving cars? These things already write code, as I mentioned. It's the weight matrix. That's the thing that you learn. You actually learn a program, and those are kind of a cartoon of where the weights might live on this thing. And if anybody wants to learn about this or talk about this, of course. These things also solve a problem that we can't solve, which is being called selectivity and variance. So basically what this comes down to is I want to be able to recognize all the features that are important to me and none of the things that aren't. And that's a hard thing to do if you're writing code. So for example, I want to write code that recognizes the difference between a wolf and a husky in the snow on grass, different pose, different age dog, different orientation. Nobody knows how to write a program that could do that, but these things do. And I think there's going to be progressively more and more machine learning and networking because it's really the only way you can deal with this deep data. And it'll be both in predictive and reactive modes, kind of, in management control and data planes, all of that, and orchestration if that's above that. And that's just simply going to change the way we design, build, and operate networks. It's going to have a profound impact, I would say, over the next few years. And again, like I said, I don't think we've really even started to scratch the surface of this. Even in the Googles and Facebooks and all of that stuff, they haven't even started to scratch the surface of this. And so it's kind of an ML revolution going on right now. It's going to change a lot of things. So that's what I got. Thank you. By the way, feel free to drop me an email. I think if you don't know how to find me, it's Google. Yeah. Thanks, Benson. Yeah, and I guess I got stuck having to be at the B&B, the beer. Yeah.
RTC web in 10 minutes.
Very interesting. Yeah, was it all right?
Thank you.
Yeah. All right.
Is that from all of the pointers it gave, which one will you recommend to start?
Oh, I'll send you the.